Hello, I'm Andrei Amatuni, and thank you for coming to my talk today, where I'll be presenting work done at the University of Texas at Austin, as well as Indiana University, under the guidance of David Crandall and my advisor, Chen Yu. In this study, we used a computational model to examine how in-the-moment visual information from infants' egocentric views determines the success of infant word learning. In this study, we'll be focusing on the role of visual sensory input. During this early learning process, infants solve a difficult computational problem in order to link spoken words with their correct visual reference. To do this, they must successfully integrate what they see with what they hear during their everyday experiences, which is challenging given the high degree of uncertainty in the visual auditory input during learning, with many candidate words co-occurring with many candidate objects across space and time. To help us understand these learning processes, researchers have long turned to computational models, which allow us to specify candidate cognitive mechanisms and computational principles inherent to this learning task. While there's been significant progress modeling early word learning using computational techniques, studies have tended to focus on idealized stimuli and subjects learning in non-naturalistic contexts. However, with recent technological advances, we've gained the ability to model infant word learning in naturalistic contexts. It's here that young infants learn their first words using high-density samples of complex sensory inputs. These advances include new sensing technologies that allow us to record infants' first-person experiences, including miniaturized GoPro-like cameras and microphones that infants can wear, as well as advanced computational models that are able to process and model the complex sensory inputs collected from these recording technologies. Prior modeling has shown that infants' first-person views contain uniquely useful information for learning. Baumbach et al. 2018 showed that frames taken from infants' egocentric views allow greater accuracy when training neural nets for object recognition, compared to corresponding images taken from their parents' view. This work showed that infants' visual input may contain a unique mix of similar versus diverse visual instances of objects, and that these unique distributional properties of the infant's visual input may account for the differences in recognition accuracy the authors report. Other work has shown how neural nets trained on infants' first-person views could predict real neural responses in ventral visual cortex, as in Zhuang et al. 2020. Critically, this study showed that data from the infant perspective, which is much smaller and more noisy data set, allowed neural predictivity on par with supervised models trained on ImageNet, highlighting the unique quality of information available to the infant learner. Infant egocentric video have also been used to simulate word learning itself, as in Tsutui et al. 2020. In this study, the authors trained deep neural nets to learn label object associations from infants' first-person views paired with parent speech. These networks learned the correct mappings without explicit supervision about which labels were associated with which visual objects. These oscillators showed that certain properties of the data, arising from different attention dynamics, had a significant impact on the model's learning outcomes, and that infant-derived data was uniquely useful for learning. These modeling studies have highlighted the unique properties inherent to infants' first-person visual sensory input and have opened up an exciting avenue of research for studying early language acquisition. However, among these studies, there's not yet been work that attempts to link these models back to human learning. Here we attempt to use these techniques to model the links between real visual sensory inputs and infant word learning. If successful, these models may allow us to predict actual infant word learning outcomes given the content of their own visual experiences, and speak to what constitutes ideal visual information for learning words. The goals of the present study are threefold. The first is to use a computational model to simulate real infant word learning in a naturalistic context. The second is to use this model to quantify the quality of visual information available during word learning. And finally, we'd like to use this model to predict individual word learning outcomes for individual infants. Here we'll present a study that takes the first step towards accomplishing these goals. Our study models the word learning performance for a set of 24 infants who were asked to play freely with a caregiver in a naturalistic home-like environment. It's in this environment that we record infants' first-person experiences as they listen to their caregiver label objects as they would naturally, while they play together with a set of 10 toys. During these play sessions, which lasted 10 minutes, infants and their caregiver wore head-mounted eye trackers recording their egocentric field of view. Microphones placed throughout the environment also captured the speech that infants were exposed to during this play session. Later, the speech was transcribed and time-locked to the video stream, allowing us to locate segments of the first-person video where the name of a toy was uttered. At the end of the play session, infants' knowledge of the names for the 10 items were tested using a screen-based task. In this task, 2 objects were presented on screen at a time, and the infant was prompted to look at the labeled object. Infants were tested on each object twice. A word was considered learned if both trials were correct, and not learned if both trials were incorrect. On average, about 2.3 objects were coded as learned, and 1.9 objects were coded as not learned. The remaining items could not be conclusively scored, as the infant did not attend to the screen for a majority of a trial, or the infant only got 1 trial correct. Here we can see examples of infant head camera frames taken from multiple different infants at the moment when their caregiver uttered the word moose. One group of frames, either A or B, is from infants who ultimately learned the object name by the end of the free play session, and the other is from infants who did not learn the name. Can you tell which group of infants learned moose by the end of the session? I'll give you a second to consider this. Here's the right answer. It's group A subjects who learned the word. As we can see from this example, it's pretty difficult to distinguish which of the 2 sets may be associated with positive learning outcomes. However, for whichever group you ended up choosing, you likely had your own internal reason for that choice. In this study, we'll train a computational model to extract patterns from these images in order to perform this discrimination for us. Here we demonstrate how a computational model can predict infants' learning outcomes above chance using only images from their field of view, taken during a labeling event. We train a deep convolutional neural network to discriminate frames from subjects who ultimately learned the meanings of these words at the end of the play session versus those who did not. By solving this classification task, our model must learn to associate visual features in the egocentric scene with the relative success of those labeling moments. And in so doing, it becomes sensitive to the visual features that constitute an ideal learning moment. For each infant, we have a stream of video frames taken from their first-person view. We select frames from this wider stream by focusing on the 3-second window surrounding the moment when the caregiver uttered the name of an object. In this figure, we highlight the moments when the caregiver uttered the name koala. And we do this for each subject, selecting all the frames centered around the 3-second window where one of the 10 toys was named. For each subject, the infant either ended up learning the mapping between the label and the visual referent, or they did not successfully learn the mapping, as determined by the end of session word learning test. For each of these frames, we label them as being either learned or not learned, based on that specific infant's learning performance. Due to differences in rates of naming and word learning for different objects, we omit half of the items from further analysis due to lack of data. This yielded 5 viable objects, which had a balance of both learned and not learned instances associated with them. We then train independent binary classifiers using a cross-entropy loss to discriminate frames taken from subjects who ultimately learned the label object mapping versus those that did not learn. For our neural net backbone, we used a pre-trained ResNet 50 model, though we found similar results using other architectures. This model was pre-trained on the ImageNet dataset and fine-tuned on our infant's egocentric scene images. To estimate the accuracy of our models, we test using 5-fold cross-validation with 3 randomly initialized training trials on each of these folds. Our classifiers successfully predict word learning outcomes above chance on frames taken from held-out labeling events, given a 50% random baseline. Our models are able to extract the signatures of ideal visual scenes from the first-person input and successfully link patterns in these signals to infants' own word learning, offering a proof of concept that this is possible in principle using a sensory-grounded computational model. We were then interested if we might be able to predict learning outcomes for individual subjects and individual objects. One expectation might be that labeling frequency should be able to account for individual word learning outcomes. However, we find that labeling frequency is not significantly different between learned versus not learned items in this study. If the amount of labeling isn't predictive, this invites us to look closer at the specific qualities of sensory experience for each individual infant and whether this might differentiate them instead. In study 2, we aggregate the field of view frames to predict learning outcomes for individual words from individual infants. Here we use the model to quantify the quality of information present in the individual infant's field of view during the labeling moment. We do this by using the model's internal sense of uncertainty in its classifications, as encoded by its confidence scores. When the score for learned classification is greater than the score for not learned, the model classifies the input image as learned, and vice versa in the case of not learned. In study 1, even in the frames correctly classified as learned, some frames may be more strongly associated with learned outcomes than others, reflecting a greater association between the visual features in that frame and successful word learning. When a frame has a large confidence score associated to it, we interpret this to mean the sensory evidence contained within the frame is more strongly associated with learning. This is because the target of the referent uttered at that specific labeling moment ended up being learned, given the specific sensory evidence contained within that frame. Each subject will have a different number of frames associated with a given word, depending on how many times that word was labeled. And this number will vary across different words, reflecting differences in the labeling frequency for that specific word and subject. And this applies across subjects, where each individual infant will have their own unique set of frames associated with the labeling for each object. For each of these frames, our model will assign a confidence score, which reflects the degree to which each frame is associated with learning that specific word, and offers a common measure we'll use to model the quality of the visual information available to different infants during word learning. Taken in aggregate across all the frames associated with the subject-object pair, these scores serve as a weighted measure of the sensory information contained in the visual input from interactions associated with that object. This allows us to study the accumulation of sensory information over time, incorporating the effects of both frequency as well as sensory quality in our modeling. In contrast to analysis in study 1, these analyses account for the entire extent of a child's interactions throughout the session, rather than just classifying single frames, and allow us to make comparisons across subjects as well as for individual objects. We use this computational measure to study how qualities of sensory experience determine early language learning. For each of the following analyses, we'll be attempting to predict ground truth learning outcomes for individual subjects and object pairs. We first look at the correctly classified frames to model the accumulation of both highly informative and ambiguous sensory evidence, reflecting the total amount of information that's positively associated to learning. We also look at the incorrectly classified frames to model the sensory information that was misleading, that is, when frames were visually similar to those from successful word learning outcomes, but where these subjects actually did not learn these words given this input, and vice versa in the case of not learned words. And finally, we looked at an integrated measure, which models the interaction of both informative as well as misleading evidence by subtracting the accumulated scores from the incorrect classifications from those of the correctly classified. This is meant to reflect the interaction of positive and negative evidence during word learning, as misleading information is integrated with high-quality visual evidence over time. For all three analyses, we find that a logistic fit significantly differentiates learned from not learned objects at the individual subject level, though we find that a model that integrates both negative as well as positive evidence is a better fit to the individual subject's learning outcomes than a model that uses only positive evidence alone. Here we revisit our original goals and review our findings. Our first goal was to simulate infant word learning in a naturalistic context. We accomplished this by collecting our behavioral data from the home lab, a naturalistic home-like environment, and then used a classification-based approach to link features of infants' first-person views to their word learning outcomes using a deep neural network. This was an initial demonstration that this is possible in principle. We then used this model to quantify the quality of visual information available to infants during word learning. We did this by using the network's confidence values to score each frame in terms of how strongly it was associated with positive learning outcomes. This offered us a measure that integrates infants' sensory experiences across time, tracking the input across the entire play session. Using this measure, we were able to predict individual word learning outcomes for individual infants, which was otherwise not possible using a more basic measure like raw labeling frequency for each object. These analyses showed that when it comes to predicting learning, all the data matters, both visually informative as well as misleading evidence. We found that a measure that integrated the misleading input along with positive evidence was a better fit to infants' learning outcomes than a model that included only a measure of the positive evidence. And for our next steps, we hope to extend these analyses to study embodied behaviors associated with the visual input, such as when infants and parents are holding the objects as they play, or when they are sustaining attention to the objects. I'd like to thank everyone that made this project possible, including all my co-authors, as well as the Developmental Intelligence and Learning Lab more generally. I'd also like to thank the funding sources that supported this work. And finally, I'd like to thank you for coming to this talk today and look forward to your questions.